All right, so let's talk about XML. As you might be familiar, XML stands for Extensible Markup Language, and it's a generic language that allows us to structure data. It became very popular at the end of last century and this century for transferring data across multiple processes. Was one of the ways that we were considering of using when we wanted to integrate disparate systems, right? Where you had a lot of folks that had legacy systems that had a lot of data just around that they were looking at how they could be perhaps shared with other folks that were outside of the enterprise. So that perhaps they were either part of acquisitions or that they were partners, or they needed to share data across the wire, and there was no way or easy way for them to just allow folks to access to their data. So they were looking for ways that whatever data they had to make it available across a network. And so we're looking for ways to represent that data in such a way that it would be standard across multiple vendors. And XML became very, very popular since it was just a plain old ASCII way of representing data. It was not proprietary. It wasn't binary. It wasn't. You could very easily create parsers that could read XML and convert it into some particular format. And it was embraced early on by a lot of heavy industry, a lot of folks at Microsoft and Sun Microsystem, Oracle, all these big players, embraced XML as a means of sharing data when it became very, very popular. At the end of the last century, when it was looking at web services as the panacea for folks to be able to integrate systems, right? People were asking themselves, how are we going to integrate all these systems? They have different database vendors. We have different data structures. You have a particular framework. I have a particular framework. You're using Java. I'm using .NET. And how do we integrate all this, right? So folks were looking at how do we create? Can we agree on a particular format that we can all share data? And XML became very, very popular. So early on, web services became very the go-to solution for wrapping an existing legacy system and providing an API that folks could send data, retrieve data from, and these web services at first the data format that they were using was XML, right? Eventually, they were kind of replaced by JSON, since a lot of the applications just started moving towards web applications, and so the data transfer slowly is converting itself to be more and more JSON. But you could still find a lot of web services where you can choose the format that you want. You want me to consume it in XML format, or do you want to consume it in JSON format? And they can speak either one, right? More and more, you see a lot of more JSON, but still, XML is still very relevant today. So let's chat about how is it that we would make data available using XML. So the idea would be at some point was to make available the data for folks that didn't have access to your data, right? Very few. Only internally, perhaps somebody could have access to the console and do some queries at to your local database, so you want to provide some APIs, perhaps some web services, some Java web services, or .NET web services, or PHP web services for folks to consume your data, and you have to come up with some structure. Obviously, not something as trivial as a tab delimited text. It has very little meta information about what the schema might be, what the data types might be, right? So this is way too low level, so we were looking for something that might be more descriptive and not ambiguous, right? So for instance, just because we have a lot of knowledge of how the world works, we can parse this and make sense out of this. That that these might be years, that some of these might be grades, and we can perhaps infer that the folks at the first column might be users, right? But a computer needs something a little more more concrete. We need some metadata that to tell us what the schema of this is. So XML became very, very popular because it allowed us to create structures that were hierarchical, right? That provided you with nodes and branches, and it allowed you to create namespaces that would allow you to break up the structure in a fairly complex manner. That somewhat were reminiscent to the data models that we were already familiar with in object-oriented technology, and so that was a plus. Also, it provided also a means of describing the data, right, by providing some metadata about the data types of each one of the pieces of data, and also the structure of that data. Right, so the XML stands for Extendable Markup Language, meaning it's a language used to describe other things, right? To not using any particular vocabulary. The language allows you to describe your own vocabulary, right? And many vocabularies are very famous today, like HTML. HTML is one particular use of XML whose vocabulary is used in the context of describing the structure of web pages. But there are an infinite number of vocabularies used in many other different domains, right? We've seen some of them, for instance, in the POM file. That's another common use in XML, where you describe the structure of a project, right? That you describe dependencies and jar files and versions, right? And that has a specific vocabulary, right? That describing a project in terms of its version history and dependencies on other projects, right? So it has a very specific vocabulary for that particular domain use, right? And there's an infinite number of vocabularies. There's for describing mathematical equations, for describing molecular biology, for describing all sorts of infinite uses, right? Of which the most famous one is HTML. HTML, and it just happens to be one particular vocabulary. And you can create your own vocabularies for whatever use that you care about. And that would be for your particular domain, right? If in your particular domain, if you're Ford Motor Company, maybe you're using it to describe a car and all the parts and pieces of a car, and the one-to-many relationships of a car having many doors and having the knobs and the nuts and bolts and how many wheels and whatnot. So the vocabulary is specific to your particular domain. And in that sense, it's meant that's what extensible means, right? That you can apply to any particular domain. Schemas, XML provides the ability of describing the structure of a document, right? That is very useful for validating the validity of a particular document, right? A document could represent a subset of a big data set, a particular data point in a large data set, or it might be representing an entire database, right? And we often like to be able to provide some meta information of the structure of that document, just like we would like to be able to describe the structure of a particular database that we might be using. We would use SQL schemas, right, where we have the structure of tables and the fields and their data types and their foreign keys and primary keys and how each table is related to other tables, yes? So we use SQL schemas to describe the structure of relational database schema, of databases, yes? Or if we use or the equivalent to that in Java, in object-oriented programming languages is classes, right? Classes allows us to describe the structure of the instances of objects that we instantiate in memory, right? And we say that this class is made up of these other classes. In that sense, XML schema play the same role, right? They describe what are the structures, what is a structure of a particular XML document, saying that certain elements must be inside of other elements, right? That has to have these particular names, and that a particular element has these attributes, and only these particular values are valid, and so on and so forth. So, and these are used for the same purposes that you use schemas, right? Schemas in relational databases typically are used for validating whether you're inserting or updating or manipulating data to make sure that whatever you are storing, whatever the data set or data point that you're manipulating meets certain constraints. Yes? Same thing when you're trying to instantiate an object in memory in Java, right? You create objects and you provide strings and integers and long and dates in their particular data type that are needed. Typically, though the validation in Java occurs at the IDE level, right? At compile time, not at runtime. So presumably, whenever you get to compile something, it has already been validated. Your IDE presumably would catch and validate all your coding based on the classes and the schema that you have defined. And similar in MySQL will catch errors when you are running or creating queries and whatnot. It'll validate against schemas. Same thing, XML, XSD, and DTDs are used for that purpose, right? To make sure that an XML document meets a particular requirement, a particular constraint, right? That you're not using an XML document that is malformed or that it doesn't have the appropriate structure. So we're going to be looking at quite a few XML pieces of document. Again, just following in the same domain that we've been looking at for the whole semester. We'll look at students and courses and sections and enrollments and university-based domains. So here's a very simple XML document, and as you might have, I'm sure you're familiar with, you have lots and lots of these pointy brackets all over the place, opening and closing brackets, and we have examples up at the top of an element called enrollments. So we say that an XML document is made up of a set of elements, right, that describe a hierarchical structure. Where here, for instance, enrollments is the root of that hierarchy, right? Enrollments is the root element of which it has these 5 branches that go off of that one root. In this case, these branches are the elements are all of the same type, which are course taken. That's the element course taken. Since they don't have any sub-elements, these course taking are also the leaves of this hierarchy. Right? So you have this root enrollments, and then you immediately have these leaves in this inverted tree, where enrollments is the root, right? And then you have these immediate leaves. Other things here that we'll see that enrollments has what is the enrollments element is implemented with an opening and closing tag. So we see the enrollments is the opening tag, and / enrollments is the closing tag. I'm assuming a lot of this is a review for you if you've seen XML documents already. But just to clarify some of the jargon and some of the nomenclature. Here we have a course taken are sub-elements of the top level enrollments element. And they have, each one of these has attributes. It looks like course taking has S name, presumably a student name. We have grad year, title, year taken, and grade A. So presumably this is a listing enrollments of multiple students across multiple courses. We see that Ian has enrolled in 4 courses. We see that they've enrolled in calculus, Shakespeare, and pop culture. And the grades are here, A, C, and B+. Whereas Ben has enrolled in Shakespeare and databases. And Ben has gotten an A- and an A on respective courses. Everybody okay? Also notice that we can infer that course taken has a particular schema, presumably. The schema is made up of S name, grad year, title, year taken, and grade. Presumably notice that they all have the same values, right? The same attributes. Those name value pairs, where S name, grad year, all those are called attributes of the elements. Okay, so an attribute is made up of multiple elements. So also taking a look at this, we see that there might be some redundancy here, right? We have some information that it looks like it's being captured multiple times, right? And remember, right? Redundancy breeds inconsistency. We're always looking for those things, right? And that's true for any particular way that you decide to structure data, whether it's UML, whether you use relational databases or Java or JSON or XML. You always have the same risk, all right? You're always looking out for cases where there might be some redundancy and there might be some risk of inconsistency. For instance, the graduation year here, right? If you can notice that that might be a problem, right? Because notice that presumably Ian is the same Ian, right? It might be some unique identifier, and that there's only one Ian in this entire enrollments. And if it's the same Ian, notice that the graduation year is being captured 3 times, right? 2009, 2009, 2009, right? And only by understanding its meaning do we know that it could be redundant, right? Because notice that grad year, the grade here, grade A, grade C, grade B+, has different values. Okay, but whereas the grad year here is 2009, 2009, 2009. Okay, now not because the values are the same do we infer redundancy, right? Not because it's 2009 all 3 times do we say it's redundant, because grade might also have been A all across. Yes, might have been A, and A. But even if the values were the same, we don't infer redundancy. We only infer redundancy because of the meaning of the attribute, right? It is okay to have grade captured 3 times because they have the potential of being different, right? You might have gotten a different grade for different courses. Yes? But whereas the meaning of grad year, it makes no sense for them to be ever different, right? You're only going to graduate once, and that value can only be the same across all 3. So by the meaning of the attribute and the value, can then you infer that could be redundant, right? You're capturing 3 times, and if that value could be different in any one of those 3, that could be an inconsistency, right? So you would look for these things. You would look for, is my data that I'm capturing, is the structure that I chose redundant? Therefore, could there be any consistency? And you would try to normalize it. So the schema that is being presented here has a flaw, right? You would say, okay, well, no, there might be a better way to capture this, right? As opposed to capturing it 3 times, because God forbid I would update one of these 3 records and not update the other 2. In the graduation year, I would be introducing inconsistency. Yes. So this schema presumably hasn't been normalized, has not been normalized. So the same problems, right, that we introduced early on in UML, then it followed us to relational databases, back to Java, right, JSONs. They're the same here, right? The same kind of questions, and we're looking for the same kind of solutions. We need to break this up, right, and see somehow if we could capture it only once as opposed to 3 times. Make sense? Right? So that's right. So let's keep looking here. You have enrollments. You have the course taken. So these are all elements. We have tags. We have the brackets and the opening and closing tags. We also say that course taken. These are all elements that live at the same level in the hierarchy. Yeah, we oftentimes say that these are all siblings of each other. Right? They're all at the same level in the hierarchy. They have the same parent enrollments, and they are all children of the same enrollment element, right? So again, this is just jargon. Also, we say that the elements course taken, they are all inside the body of the elements of the enrollments elements, right? So we say that the enrollments has a body. The body contains a whole bunch of course taken. Yes, but notice that course taken itself doesn't have a body, right? It doesn't contain any sub-elements. Well, enrollments contain sub-elements, but the course taken themselves don't have any sub-elements. So we say that it has no body. It has no body, and so notice that it has a slash at the end, right? So we say that it's represented by a self-closing tag, right? So it doesn't have an opening and a closing tag. It's just a self-closing, right? It opens and it closes itself with at the end of the slash at the end of that closing tag, right? All right. So what else? So we have all the elements where it must. Yeah. Right. So one of the things that we have to make sure is that the document at least is well formed, right? We're not saying anything about the data itself, but it has to be well formed at least. In that, for instance, we have an opening and closing tag, right? That everything has an opening and closing. At least here, if it doesn't have a body, that it's self-closing. Right? What else? If you have a nesting where you have opening, you have multiple elements that are nested inside of another, that they don't overlap, right? That they're all inside of each other, right? That elements are all well inside of each other. So we'll take a look at that, examples of that. Right. So here's an example on taking a look at the problem we had earlier about the graduation year, right? This was presumably all these folks, Ian and Ben. Notice that they were all graduating in 2009, right? And so this presumably is the graduation year 2009, and it was being captured 5 times that all these folks were graduating in the same year. So to normalize it, there's a couple of options that we might do. For instance, what we could do is capture the graduation year only once, right? Just perhaps move that attribute up one level, right? Maybe to the enrollments elements, right? So that would fix our denormalized schema, right? We could capture that graduation year only once by capturing at a higher level instead of capturing multiple times. So now we can say that this is a normalized schema, right? That it doesn't have any redundancies. There's only one place where we can capture that and modify it, right? And there's no way to make a mistake, right? Now notice that the normalization strategies are fairly different, right? In the normalization in a relational database, the strategy was typically to split it off into multiple tables, right? And then have a relationship between the two, right? Here, the equivalent of breaking up one table and another table is to have hierarchies, right? To have a hierarchy inside of another hierarchy. The relationship between entities, right? The relationship is by having entities nested inside of other entities, right? Very much like Java. Right? In Java, the way you capture relationships, like for instance a one-to-many relationship between a parent and a child, was to have the child be an attribute of the parent class. Yes? Right? So similarly here, right, the way you capture the relationship between courses and the enrollments is that enrollments live inside the body of their parents. Yes? So that's the way you normalize in XML, right? To create hierarchies as opposed to breaking it up into different elements and then somehow referencing each other. All right. You can also have references in XML, but it's less common. Right? More typically, the relationships is captured by embedding child elements into the body of their parents. Also, we're going to be talking about schemas that are fairly flat, like this one. Right? It looks, it's only because we have perhaps a root and then immediately we have the leaves. Right? There doesn't seem to be any branches in between, right? That's, we said that this is hierarchical, and so now the depth of the hierarchy it speaks to how normalized or denormalized the schema might be, right? Where perhaps notice that in the course taken we're capturing lots of information for that course. We're capturing Ian, or we're capturing the title, the grade, the year taking, and whatnot. And some might challenge this schema and say, wait a minute, you're capturing information about the student and the course, in the same element, right? So you might say, this perhaps a better representation might be that instead of capturing Ian 3 times, right, and capturing Ben here twice, perhaps a better representation might be that you capture Ian, the student, just once, and then perhaps nested in there might be all the courses that Ian took, right? And same thing for Ben, right? So again, the same questions of first, second, and third normal form, right? Of splitting off, into multiple tables. Here, the equivalence is to splitting it off into nested hierarchies. Okay, so this particular representation is fairly flat. Now, an equivalent representation might be the following, right? Where you might have perhaps a list of all the graduating students, and then multiple lists of various students. For instance, you might have, instead of having one element capturing courses and students, you might split it off and say, well, I'm going to capture the student level. I'll capture all the information about the student at that level. Okay, all the children elements of the student might have the name and the graduation year, maybe my GPA, my full address, my email, things that are that pertain to the user, to the student entity, of which one of the entities might be all the courses, my transcripts, right? All the courses that I might have taken throughout my stay at that particular university. Where you have courses that then list multiple courses and the particular year that I took that course and the grade that I took for that course, right? So I might have here course, the title and taken year, and then a list of all the 3 courses that I took, and then Ben would have its own entry, right? And then the list of courses for Ben. So if you compare this particular representation to this other representation, you could already see that perhaps this is a less normalized schema as compared to perhaps this one over here. Right? That there's a much deeper hierarchy of the structure of the data, but perhaps it captures identical pieces of information. Yes, just like you would have an equivalent relational database. That might capture the equivalent information of some other relational database, right? Different structure, different UML class diagram, but it might be the same information. Perhaps one more normalized than the other. Perhaps one having more redundancy than the other. Yes? Oftentimes, this also is relevant when perhaps two equivalent universities or 2 equivalent entities want to be able to perhaps automate some of the information that they share amongst themselves, and they want to share and send over data, that might be represented one way in one institution and represented in a different way in some other institution, right? They have to agree. They have to somehow agree, on what is the schema on how they're going to do transaction. Right, that what I mean by student means the same thing to you, right? What I mean by courses may have the same meaning to you, right? So we have to agree on a vocabulary, right? That I call the titles of the names of my courses. I use the title element, right? And I use the year taken and the grade. It has a meaning in my schema. Hopefully, it will have the same meaning in your schema. We have to agree on a schema. Otherwise, we'll need to agree on some kind of transformation, right? On your interpretation of your data in your schema and how it might be transferred and converted into my own schema. We'll talk about that a little later using XSLT and data transformation. Anyway, so here's a hierarchical graph representation or tree representation of the data we're looking at. We have the root element at the top, graduating students, and then we have presumably a collection of students, each one with its own branches, right? Where you have student name, graduation year, and then the course list, then listing several courses, and then at the leaves you actually have the data. Right? The data is Shakespeare, calculus, and whatnot. So the data lives at the leaves of these trees, right? Whereas the branches represent relationships, right, between the entities, between the data points. Right? So branches represent relationships, whereas data is at the leaves of it. So this is roughly equivalent to in relational databases where you use foreign keys and primary keys to construct the relationships between records. Right? So the way you build these hierarchies in relational databases is to create foreign keys and primary keys. You follow along, you navigate, right, through the branches by following the primary key, the foreign key to the primary key, and then the foreign key to the primary key, and so on and so forth. Right? That's how you navigate. Here, you navigate by following these branches along the hierarchies. Make sense? Okay. Yeah. Okay, so let's take a look at some hands-on on how you would work with XML documents using, in particular, the Java programming language.